Everyone. Welcome to the fourth seminar in the Distinguished International Speakers List series arranged by the Consortium for Quantum Condensed Matter, East and North India. So it is my great pleasure to introduce our speaker today, Professor Stephen Kivelson, one of the most influential theoretical physicists of our time. Professor Kivelson is the Prabhu Goel Family Professor of Physics at Stanford University and a leading figure in the study of quantum materials, particularly strongly correlated electron systems, high temperature superconductivity, and quantum phases of matters. Over several decades, his work has shaped our modern understanding of complex quantum systems. He has made seminal contributions to topics ranging from nematic order in electronic systems to physics of cuprates, topological phases, and unconventional superconductivity. His insights have often provided the conceptual foundation for experimental discoveries, and his papers are among the most widely read and cited in condensed matter theory. Professor Kivelson is a fellow of American Physical Society and a recipient of numerous prestigious honors such as Guggenheim Fellowship, election to the American Academy of Arts and Sciences, and the US National Academy of Sciences, the John Bardeen Prize, and very recently in 2025, Oliver E. Buckley Prize. Today, he'll speak to us on emergent gauge fields in quantum condensed matter, and we are very fortunate to have him with us. Please join me in welcoming Professor Stephen Kivelson. So yeah, sir. So I'll request the audience to just keep their questions for the end. If you have some pressing question, you can also ask him in between. With this, I'll just ask Professor Stephen Kivelson to start his seminar.
All right, thank you. And thank you for that very nice introduction. Yes, I'm going to talk about emergent gauge fields in condensed matter systems. This is work to the extent that it's original. Much of it isn't, but to the extent that it's original, it's work that I've done with many people over many years. The top line are people that I've worked on recently, but I'm not sure I'll get to this most recent work. It depends on how fast we go. So fundamental gauge symmetries have, when I was a student, they were described in semi-religious terms. Maybe rhapsodic might be a better description. And I looked up and I found some quotes from famous physicists that sort of reflect the way gauge symmetries were taught to me when I was a student. Here's from Paul Dirac. The gauge principle reveals a hidden harmony in the laws of physics. One feels that such mathematical beauty must be a reflection of nature's inner structure. Or here's Xian Yang. It is profoundly significant that the symmetry group dictates the dynamics. Gauge symmetry is not a feature imposed upon nature, it is nature. Or Steven Weinberg, who actually I took quantum field theory from, in all of physics, nothing is more beautiful than the principle of local gauge invariance. All right, so I have to say I never really understood this. So I understood what gauge invariance meant. For instance, we're familiar with it in the electromagnetic contexts, where it says that all physical properties of the system are invariant under a gauge transformation, which shifts both the gauge fields and, in quantum mechanics, the phase of the wave functions. And chi of r and t here is an arbitrary function of r and t, so it's viewed as a local symmetry. In classical electromagnetism, this reflects just a mathematical convenience, and that one is characterizing electric and magnetic fields in terms of gauge fields for mathematical convenience, but there is a redundancy in the description. In quantum mechanics, this gauge symmetry is much more fundamental, and in particular, one elevates the gauge fields themselves to be the dynamical variables of the quantum field theory. And then gauge invariance implies extremely powerful constraints on the form of the action that governs the quantum dynamics. So it gives once one assumes that the universe has a local gauge invariance, there are a lot of beautiful things that follow from that. But it's not obvious why nature should have this very bizarre local symmetry. At least it's never been obvious to me. Emergent gauge theories are something that we've come to appreciate more recently, and these at least make sense to me as a condensed matter physicist versed in notions of emergence. So the idea of an emergent gauge symmetry is that when there is no microscopic, that is to say, no exact gauge symmetry, but the most efficient description of the low energy physics requires that we introduce a gauge theory description of the physics as if the system had a fundamental gauge symmetry. So let me describe in broad brush how this works. So to begin with, being a condensed matter physicist, I'm much more comfortable when we write down a theory on a lattice. So we write down a Hamiltonian, which is gauge invariance. It's a lattice gauge theory with dynamical gauge fields. And this we can treat as a problem in statistical mechanics, as was first done by Franz Wegener in the early 70s. And what one finds is that this model has two phases, but there is no local order parameter that distinguishes them. There's no broken symmetry associated with them. They are instead a confining phase and a deconfined phase. And it was also shown not much after that by Fratkin and Schenker that the confined phase is also what we now call a Higgs phase. And there's a deconfined phase which has free fractionalized quasiparticles, which you might think of as being quarks, and possibly propagating photons. The photons in the Higgs phase would be massive. So that's fine. That's put things on a lattice, but so far it's no different than what one does in with the fundamental gauge theories of nature. But now here's the interesting thing. If we take our Hamiltonian, so H naught is the lattice gauge theory that I've just been describing, but if we perturb it with any other local perturbation, including H primes that have no gauge symmetry whatsoever, we find that the two phases of the gauge theory are stable in the presence of small perturbations. That is to say, the gauge symmetry breaking perturbation is irrelevant. Now, inverting the logic, what that means is that if I start with this Hamiltonian, H naught plus lambda H prime, which is not gauge invariant, the low energy physics can be described as if I drop the lambda H prime. That is to say, as if I had a gauge theory. And so there are two phases again. Now, if we're in a strongly confining phase where the gauge field fluctuations only occur at very high energy and short distances, then what I've said is a mathematically correct statement, but it doesn't teach us anything. In fact, it's possibly even misleading. It means that we introduce some high energy degrees of freedom, which we then immediately wanted to ignore because they have no effect at low energy. However, if we're in the deconfined phase, or even in a limit of weak confinement, as is the case with quarks, then we will have a much easier time understanding the physics if we approach it from this gauge theoretic description. So now I'm going to talk only about things I know about, which is how emergent gauge theories apply, how they emerge, and what we learn about them to the low energy physics of condensed matter systems. But with this introduction, I can't refrain from pontificating slightly and commenting that to a condensed matter physicist, and I think to an increasing number of high-energy physicists as well, it seems reasonable to imagine that even the fundamental gauge symmetries, like those that underlie QED and QCD, are themselves simply emergent symmetries of some high-energy theory that may not be gauge invariant at all. All right, that's the end of my pontification. You can ignore that if you like. Let me talk about examples of emergent gauge theories that we'll encounter later on in this lecture that occur in condensed matter systems. So probably the best known is the Chern-Simons description, the Chern-Simons field theory descriptions of fractional quantum Hall states, and then various gauge symmetries, either Z2 or U1 gauge theories of quantum spin liquids. In particular, what we'll see is that although in many cases we could treat these problems in other ways, treating it from a gauge theory point of view gives us an elegant way to treat the fractionalized excitations in these systems, that is to say the fractional Laughlin quasiparticles in the quantum Hall effect, or the spin-ons and holons in a spin liquid, and allows us to understand why these particles, under many circumstances, can have fractional statistics, that is to say they're anyons, why there are associated with these phases certain topological degeneracies, and how we could get new collective gapless modes, that is to say an emergent photon. So that's our goal. Now, I want to raise a note of caution. Once people in condensed matter physics got the idea of emergent gauge theories, people went a little crazy and they saw them everywhere. And in particular, you can introduce emergent gauge symmetries as a mathematical device, even when it doesn't correspond to the physics. So the most common way of doing that is by rewriting theories exactly in terms of parton constructions. This used to be called slave particle constructions. So this is something you can do. So for instance, if capital psi sub sigma is the field that creates, say, electrons at position r and t, and suppose those are the only physical fields in my problem, but I could formally write this as the product of a fermionic field, little psi, and a bosonic field, capital phi. Why might I want to do that? Well, in some strongly correlated systems, one might imagine that there's a non-holomorphic constraint on the electron occupancy, for instance, that a site may be occupied only by 0 or 1 fermion electron. So there's this inequality that psi dagger psi must be left center equal to 1. And it's hard to deal with constraints like that. Whereas in terms of these new variables where little psi is called the spin-on field and capital and little phi is called the holon field, this constraint becomes that every site is occupied either by a spin-on or by a holon. And this description is redundant. That is to say, there is a gauge transformation I can make. I can introduce an arbitrary function, chi of r and t, and shift my fermion fields by a phase, my boson fields by the same phase, and under this transformation, my physical fields don't change. So that's an exact gauge symmetry of this new description. But that's really just a statement that I've made a sort of awkward description of the electron in terms of extra degrees of freedom. So although there's an exact gauge symmetry, this is a mathematical trick. It's only if the physics reflects this that this is useful. Another way of putting it is that if you write this as a gauge theory, it's a gauge theory in which at least the bare gauge coupling is infinity. There's no Maxwell term this gauge field. Not only that, I could go even more nuts. Rather than writing this as the product of a fermion field and a boson field and getting a U1 gauge theory, I could have been fancier and introduced a non-abelian gauge symmetry. So I could have put an index on my fermionic field and on my bosonic field, which I sum over. So this repeated index alpha is supposed to be summed over. And then my gauge symmetry is I can make any local unitary transformation I want on small psi and the same unitary transformation on little phi, and all my physical degrees of freedom are unchanged. So I tell you that my favorite interacting electron problem is actually an SU12 gauge symmetry theory in disguise. Obviously, that's not particularly useful. So what we would like to do is understand how emergent gauge theories come out, not out of fancy mathematics, but out of clear physics. So what phenomenological observations would call for a gauge theory to describe them? So now I'm going to give you an outline of how I'm going to introduce these notions. To begin with, I'm going to talk about fractionalization and its relation to topology in one dimension. It turns out in one dimension there are no non-trivial gauge theories, so this is just a warm-up step, but most of the notions that we're going to need, most of the phenomenological notions, we can see in this 1D context, and they're very much simpler to understand in this context. They can be understood entirely with pictures. Then I'm going to go to the best characterized example of a problem that has a gauge theory, an emergent gauge theory description, which is the fractional quantum Hall effect. And I'm going to start by generalizing some of the notions I developed in one dimension to show that once you have the fractional quantum Hall effect, you inevitably have quasi-particles with fractional charge and fractional statistics. I'll make similar constructions for spin liquids. And then, if time permits, I will discuss some more recent work where we found that spin liquids really don't require spins or even magnetism. And so this is an observation that allows us to search for spin liquids in a much broader class of materials, in particular just simple systems with strong electron-phonon coupling could give rise to spin liquids. So I may or may not get to this red point. All right, good. So let me start unless there are any questions. All right, so I'm going to start by describing a one-dimensional polymer called polyacetylene. I studied this as a postdoc of Bob Schrieffer's. And here in the upper right-hand corner, you see a picture, a schematic picture of a polyacetylene polymer. The dots are supposed to represent carbon atoms. Dangling off of each carbon atom is an unshown hydrogen atom. And the polymer can form one of two possible ground states which break mirror symmetry. Either, as in the upper row, it can form alternating short and long bonds where the short bonds are pointing up to the right, or as in the lower picture, it can have the short bonds pointing down to the right. The arrows show the direction of the motion of the carbon atoms in this broken symmetry state. And you can see that by symmetry, the energy of these two states must be equal to each other. So there are two degenerate ground states. It reflects spontaneous breaking of a discrete symmetry, in this case, reflection symmetry. I'm going to straighten out these pictures because it's too hard to draw these zigzags. So here's a picture of a undistorted polyacetylene chain before it goes into its broken symmetry state. And then below that is a picture, the schematic picture of the broken symmetry state, where the dark bonds are supposed to be the short bonds, where the coupling between the sites is stronger and the electrons can hop more easily between the sites with the dark bonds than with the light bonds. So here's a schematic picture of the ground state of one of the ground states of polyacetylene. Now, because this is a broken symmetry, it makes you think of an Ising model, and the natural topological defects in an Ising model are a domain wall. So here's a picture of a domain wall. To the left, I have one form of the broken symmetry state. To the right, I have the other, and in between them, there is a domain wall, a discommensuration between these. And so this domain wall is an interesting excitation of the system. It's a soliton, and as you can see in one dimension, it has the feature that it's a point-like particle. So that's the Ising domain wall, or the Z2 soliton of this broken symmetry state. Now, here's what's interesting. We can show that this excitation has fractionalized quantum numbers. And this is an argument that was put forward by Bob Schrieffer, and it's called the Schrieffer counting argument. So let's imagine that we have spin polarized electrons or spinless electrons. So we have just fermions with charge E. And let's go to the strong coupling limit, where the strong bonds are strongly coupled, but the weak bonds are zero. So then what you can see is on every strong bond, there will be a bonding and an anti-bonding orbital, and we'll put one electron in the bonding orbital. So this allows us to associate with each strong bond one electron. So I now can count electrons. I just look at the number of strong bonds, and that tells me the number of electrons. And now what I'm going to do is remove one electron from the system. So I've just done that. I've removed this bond with its electron, and okay, good. But now what I can do is I can look at this as being two solitons next to each other. So I've got charge E here. Nobody has any doubt about that. But now what I'm going to do is I'm going to move these two solitons apart. So here I've moved them apart. And now what you can see is that I've taken this excitation and broken it up into two identical domain walls. Both of these are Z2 domain walls, so each of them must have half the charge. And so each of these domain walls has a fractional charge E over 2. And then the argument goes, now once I've established that, if I now go back from this strong coupling limit and don't treat the red bonds as being zero, but as being small, as long as I don't close a gap in the spectrum, the charge identifications won't change. I can do the same analysis dealing with electrons with spin. Now, when I've taken out one bond, I've taken out two electrons. I have one electron of each spin in the bonding orbital, so I've taken out charge 2e and spin 0. I then separate these, and so I now have charge E and spin 0 associated with each of these solitons. That's still a fractionalized excitation, because for electrons, you have charge and spin are tied to each other. So you either have charge E and spin half, or charge 2e and spin 1 or spin 0, but you can't have any combination of electrons that is charge E and spin 0. I could also, for instance, add one electron back to this soliton, as I've done here. That changes the charge by 1, so I now have charge 0, but spin a half. So again, I get another fractionalized excitation, the spin-on, which has charge 0 and spin a half. So the fractionalization shows up as spin charge separation. And it turns out that in polyacetylene, there's really direct experimental evidence that the solitons occur and that this fractionalization occurs. And I've given you a reference here where this is summarized. Okay. Now, here I had a period 2 charge density wave, which had 2 degenerate ground states. If I had a commensurate Q, say Q equals 2 is what I've shown, but Q equals 3 or Q equals 4, I could do the same sort of Schrieffer counting argument, and I would find that in the presence of spin, the soliton will have charge 2e over q plus any integer number of electrons that I might want to add to it. All right, so now this argument is great, but it was very controversial at the time. All sorts of, in particular, high-energy physicists doubted that this fractional charge was a sharp quantum observable. They said that this counting argument was fine, but consider the following problem. Suppose I had 2 hydrogen ions, 2 protons, and 1 electron, and so I put the electron in the ground state of the 2 protons, and then I pulled the 2 protons apart so that they are more than a hydrogen radius apart. So then the ground state would look like this. The electron ground state would look like this. The electron would be equally distributed on the 2 hydrogens, which means that the expectation value of the charge on the left hydrogen would be 1/2. But this isn't a sharp quantum observable. If I calculate the mean squared charge on the leftmost hydrogen, that's also e squared over 2. It's 50% probability that there will be 0 charge on it and 50% that there will be charge 1 on it. It's not that there's ever charge 1/2 on it. This fluctuation is as big as the average. So the charge on the left, this fractional charge, is not a sharp quantum observable. And the physical reason for this is that the electron, in this case, in its ground state, is in the bonding orbital, the symmetric orbital on the 2 hydrogen atoms, but the splitting in energy between the bonding and the anti-bonding state drops exponentially with the distance between the 2 protons. So if the protons are far enough apart that their charge clouds are disconnected, as I've shown in this picture, then the bonding anti-bonding splitting is exponentially small, and any experiment that we do will collapse the wave function and give us either charge 1 or charge 0 on the left hydrogen. Okay, I said that. I should have been showing these, but I've said that, so I'm going to go on. So that's not what happens in polyacetylene. In polyacetylene, I can write down a Hamiltonian that describes this problem. Here, T sub j is the matrix element that hops an electron from site j to the site j plus 1. And in this ground state, T sub j is dimerized. It's larger Tj, T equals T plus delta over 2 on all odd numbered sites, and it's smaller T minus delta over 2 on all even numbered sites. And this gives rise to a spectrum in 1 dimension. Here's the density of states on the vertical axis and energy on the horizontal axis, which has a valence band, a conduction band, and a gap of size delta at the Fermi energy. So there's a gap in this spectrum. It's a semiconductor. And then if I do the same thing in the presence of a soliton, so in the presence of a soliton, the hopping matrix elements are positive or negative depending upon which side of the soliton you're on, it leaves the spectrum more or less the same, but it introduces a bound state at 0 energy, the so-called mid-gap state. But for the charged soliton, either this state is empty or occupied, so there's still a gap delta in the spectrum. And because the gap persists even when the 2 solitons are well separated from each other, it's possible to measure a fractional charge. And so one can define a charge operator. This was done by Bob Schrieffer and me, and slightly later by Rajaraman and Bell. And you can show that this is a sharp quantum observable with an eigenvalue which is fractional. Okay, so now I've talked about fractional charge. We're sneaking up on gauge theories, so let me discuss the implications of fractional charge for gauge invariance. And this is a thought experiment that Martin Rochek and I did went through in 1985. So imagine you have a system, maybe it's a one-dimensional system, maybe it's some more complicated system, but it has a fractionally charged quasiparticle with charge E over Q. And suppose I orient this system, I construct this system, so I wrap it around in a circle like this, and I thread some electromagnetic flux phi through the circle, such that there's no magnetic field in the system, there's just flux going through the system. Now, fundamental electromagnetic gauge invariance implies that if I change the flux through this circle by any integer times the quantum of flux, hc over E, that no physical observable of this system can sense that. So everything about the spectrum is invariant under that. That's what phi is equivalent to this means. Now, on the other hand, if I try to write down a wave function for my quasiparticle, I will find that as it goes around, it picks up a phase determined by the effective flux quantum, hc over q, which is q times phi naught. So if q is bigger than 1, say if I have a charge a half or a charge a third, then I violate gauge invariance. I put through one flux quantum and the spectrum of my particle changes. So the only way to fix that is to allow the wave function of my quasiparticle not to be a single valued function, but to be a q valued function. So it only returns to itself after the quasiparticle goes q times around this circle. Now that sounds somewhat artificial and strange, but let me show you how it arises very naturally from the topology of this fractionally charged particle. So here, let me imagine I've taken spinless electrons in polyacetylene, and I've put a soliton at one point, and I've bent my polyacetylene ring around my flux like this. So up here, I'm showing a close-up of this front of the ring, and down below, I'm going to show you the ring. And now what I'm going to do is I'm going to start moving the soliton around the ring. So first here, I'm going to keep a record. This is the state I started with. And then what I'm going to do is I'm going to move the soliton one step to the right. You can see it's moving around the ring below. Up here, you can see that it's moved one step to the right. And then I move it another step to the right. And then I move it another step to the right. And, well, now it's gone behind, so I don't see it anymore. But now I move it back around and it appears from the other side, and good, I've gone all the way around. But what you can see is that although I've gone once around, I haven't returned the system to its original state. And now I have to go around again, so I'm moving it to the right, I'm moving it to the right, and now I've moved it behind, and now I move it back in and back in. And so I can only get back to the same state after I've taken it twice around the ring. So gauge invariance required that I have a double-valued wave function. The topology of the soliton implies that I have a double-valued wave function. So everything is okay, only because my fractionally charged quasiparticle is also a topological excitation. All right, so now let's finally get to places where gauge theories really occur. Let's look in dimensions bigger than 1, and so let's start with the fractional quantum Hall effect. Now, I'm going to make an aside. I don't know how many experts there are in the audience, but it turns out that this one-dimensional analysis that I went through is actually not completely decoupled from the two-dimensional physics of the quantum Hall effect. One can imagine defining the quantum Hall effect on a torus. Here is the torus, so my electrons are supposed to live on this torus. B is the circumference of the torus around, and A is, the size of the donut. And I'm going to go to the thermodynamic limit, letting A go to infinity. So I'm still talking about an infinite number of degrees of freedom, but I'm going to take the limit where B, the radius of the circumference of the torus, is much less than the magnetic length. And in this limit, it turns out that the physics of the fractional quantum Hall effect and the physics of these fractionally charged particles in a commensurate charge density wave in one dimension map exactly onto each other. And so as long as there's no phase transition as a function of B, which at least there's good numerical evidence that there isn't, then we could understand everything about the two-dimensional fractional quantum Hall effect by studying it in this narrow torus limit. And that was worked out by Bergholz and Karlhede in 2008. Okay, so that was an aside. Let's deal with two dimensions and the fractional quantum Hall effect. So the first thing I'm going to explain to you is that once you've observed the fractional quantum Hall effect, you automatically know that you must have particles with fractional charge. And since fractional charge implies fractional statistics, they also must have fractional statistics. So let's go through this argument. Now, and then I'm going to ultimately, after showing that, then I will have provided the phenomenological driving force that says I need to give a gauge theory description, and I will do that by introducing a Chern-Simons gauge theory. All right, good. So I'm going to show that fractional quantum Hall effect implies fractional charge. Now, the argument that I'm applying is an argument that was introduced in his brilliant first paper by Bob Laughlin, but he applied it backwards. So what I'm going to do is go through exactly the arguments that Bob Laughlin went through, but I'm going to do them backwards. I'm going to say, assume we had a system that exhibits the fractional quantum Hall effect. So that means it's a state that has the following characteristics. The longitudinal conductivity is 0, so there's no dissipation in the system. And the Hall conductance is quantized. Sigma xy is 1 over q, where q is an odd integer, times e squared over h. And moreover, that the system is incompressible. That is to say that there's a gap in its spectrum. So that's the fractional quantum Hall effect. And now what I'm going to do is the following thing. I'm going to take a plane that has the fractional quantum Hall state in it. I'm going to drill a little hole through it, and I'm going to thread flux through that hole. So that's what I'm doing here. Now, as we thread flux through that hole, we generate a EMF, and the EMF is, of course, proportional to the time derivative of the flux and inversely proportional to how far away I am from the hole. R is the distance from the hole. Okay, now, because I'm in a system that has a Hall conductance, when I have an EMF that's pointing around the circle, it means I have a current that's flowing outward. And so I can integrate that outward current to see how much flux, how much charge am I accumulating in the neighborhood of this hole. And that's what this equation says. Q dot, the amount of charge near this hole, is equal to the Hall conductance times phi dot over c. And now what I can do is I can crank up the flux until I've put one flux quantum through. Now I've returned the system to the original Hamiltonian. A quantum of flux is undetectable, so it's the same problem that we started with, but I've gotten into a new state because the new state has some charge that's accumulated near the hole, and looking at this equation, it's easy to see that that charge is just E over Q. So this proves that if you have the fractional quantum Hall effect, you must have excitations of the system that have fractional charge. Okay, well now let me repeat the argument that we've just gone through. If we have fractional charge, then let's do the following thing. Let's first put our flux through and generate a quasi-particle at the origin. Let's introduce another quasi-particle somewhere outside of that, and then let's carry that quasi-particle around the outer quasi-particle around the inner quasi-particle. Since there's flux phi naught through this hole, the phase that the wave function picks up is 2 pi over q, which is to say that the wave function is multi-valued. The quasi-particle has fractional braiding statistics around each other. Okay, so that makes psi a multi-valued, a q-valued wave function, which is described by fractional statistics. Okay, so the way we describe this, okay, now I'm going to do, to begin with, exactly what I told you we shouldn't do. I'm going to do mathematics. I'm going to do an exact transformation. It's exact. It's going to exactly transform this problem into a gauge theory. This is useful because the gauge theory is something that looks very physical, but really, truly, the exact transformation is misleading. It's that the answer that we get is the right answer. Okay, so here's what we're going to do. We're going to take our many fermion wave function. So psi is a many fermion wave function. So it's odd under the interchange of any two particle coordinates. And we're going to write it as a unitary operator times another wave function of the many particle coordinates. And this unitary operator is going to be the exponential of e to the I alpha times theta, where theta is the azimuthal angle between particle I and particle j. All right, so that's a unitary operator. Theta, of course, is not a single valued function. It's only defined modulo 2 pi. So this unitary transformation is only single valued if alpha is an integer. So I can only do this for alpha equals an integer. But if alpha is an odd integer, then if I interchange two particles, I change theta by pi. And so u is odd under interchange of any two particles. So if u is odd, and psi is odd, phi has to be even, which means that phi has to be a bosonic wave function. So this unitary transformation changes bosons to fermions or fermions to bosons. Its operation on other operators is rather simple. On the position operator, it leaves it invariant. On the momentum operator, it shifts it by a statistical gauge field little a of r, where little a of r is the gauge field that we would get if we attached alpha flux quanta to every particle in the system. So here, rho of r is the particle density. So this is the flux attachment transformation that says I'm going to introduce a statistical vector potential, little a of r, that corresponds to the magnetic field associated with attaching alpha flux quanta to every particle. And then I'm going to introduce a time component of the gauge field as a Lagrange multiplier to enforce this constraint. And then I can allow little a to be a dynamical gauge field where there's a dynamical electric field as well, which is given by the usual expression, and it's easy to see that that's just alpha times phi naught times the particle current. And I can now write down a new Lagrangian that describes this problem in terms of a bosonic field phi coupled to the sum of the statistical gauge field and the electromagnetic gauge field, where instead of a Maxwell term for the statistical gauge field, we have what's called a Chern-Simons action, and I won't even bother to write it out. It's too many equations, but there's some simple expression there, and this is an exact rewriting of the problem. as a problem of composite bosons.
We have 15 more minutes. 10.
15 more minutes. Perfect.
Yeah.
Okay. So now, so this is exact but useless. But now if I treat this as an effective theory, that is to say, if I say, all right, I'm going to just look for, say, saddle points of this, and that's a leap. Then I find that if, for instance, the bosons are going to condense into a Higgs phase, then that exhibits a Meissner effect. So that requires that the total magnetic field that the bosons see is 0. And since little b is the charge density, this means that the charge density must be 1 over alpha in units of the flux quanta. So it means the system is incompressible, it has a gap, and since it's a perfect conductor, the electric field must be 0, and this translates into the Hall, quantized Hall effect. So this gives us a very powerful and simple description of the quantum Hall effect, just in terms of familiar phenomena from gauge theories, the Higgs phase. And in particular, then, the flux quantization that we get in a superconductor translates into the fractional charge and fractional statistics of the quasi-particle. All right, so since I'm running light on time, let me skip this. Yeah, so, all right, so this gives us a very nice way of treating the problem. It doesn't really give us anything new at this point. These are things that Laughlin and other people had computed directly in terms of electrons, but it does allow us to try to approach more complicated problems, such as critical phenomena associated with phase transitions between different quantum Hall states, transitions between quantum Hall and quantum Hall pneumatics, and probably most useful of all, using the same sort of transformation, not in terms of composite bosons, but in terms of composite fermions, to understand the properties of the very mysterious composite Fermi metal. So this gauge theory approach is very powerful and has been very fruitful. Good. All right, so I'm going to start now on spin liquids, but are there questions before I proceed?
Yeah, I think we take it at the end. We don't have.
Okay, it's very strange talking into a vacuum. I have no idea whether I've completely lost everybody or everybody is following.
We are here. We are here. Very much.
Let me continue then.
Yeah.
So let me show in more concrete terms how a gauge theory can arise. And in this case, I'm going to construct a very simple model that turns out to be a Z2 gauge theory. So here what I'm going to do is to consider the quantum mechanics of the following problem. My degrees of freedom are little hardcore dimers, which I've shown over here, and they're going to live on some lattice, which I've shown to the left. And so I put them on the lattice, and because they're hardcore, they can't overlap. And I'm going to put them at the maximum density that's allowed. So every site is touched by at least by exactly one dimer. And so here are two possible configurations of my dimers. I allow my dimers to be either on nearest neighbor sites or second neighbor sites. We could generalize it further if we wanted, but this is complicated enough. And here are two pictures of, so these are, each dimer configuration is going to correspond to a quantum state labeled by the configuration of the dimers. And so then eigenstates of whatever Hamiltonian I'm going to write down are going to be written as superpositions of these dimer states, like this, and different states are characterized by different wave functions psi of c. This state is probably a snapshot of a state that's important if I made a dimer liquid. The dimers are sort of all willy-nilly. And this is a snapshot of a state if the dimers wanted to order, they've broken a symmetry and formed a dimer crystal. And then I'll have some Hamiltonian which will induce some local dynamics on the problem. For instance, I might have a dynamical move in the Hamiltonian that connects this state with a state where I've flipped two dimers. That still respects the hardcore dimer constraint, and so that sort of dynamical move is allowed. And here's another sort of dynamical move. I can flip these dimers. I can flip those dimers. I can flip those dimers. And so there's all sorts of dynamics. And after I've applied the Hamiltonian a few times to the system, I end up with states like this. And one of the things about the liquid is after stirring it up, it looks more or less the way it did before, whereas in the crystal, I can see that I've made defects. And so probably if I ran the dynamics for longer on this right-hand state, it would move back towards the original configuration, where this, on the left, the liquid state would continue stirring. Now, let me see what the Schrieffer counting argument tells us in this context. So let's remove one dimer. Here I've removed one dimer on each side here. So I've removed two electrons and spin 0 and made two empty sites. And now I'm going to let the system stir up under its own quantum dynamics. So for instance, I'm flipping bonds like this and I'm flipping bonds like that. And sure enough, after a while, I've separated these into two separated holons. These are fractionalized excitations that clearly, since the original dimer had charge 2 and spin 0, these have charge E and spin 0. But there's a big difference in these two states. In the valence bond crystal, I can see that in order to separate them, I've made lines of defects in the crystal. I've got lines where the system is not in its preferred state, so the energy must be growing linearly with the separation between these two defects. So these two defects are confined. If I now allow the dynamics to run longer, these will necessarily, like a spring, come back and recombine. Whereas these two are separated by liquid. It's no different than liquid was before, so these holons are deconfined. This state also has a topological degeneracy, which is basically the primitive version of a Z2 gauge structure. That was shown by David Dowless in 1988. And the argument goes like this. Suppose I had the ground state of this system, which I've written down here as psi, and then suppose I write down another state as follows. I draw this line along a bond that goes all around the system, and I take the same wave function, but I multiply it by e to the I pi times n, where n is the number of dimers that intersect this line. So in this picture, that's 4. So e to the I pi times 4 is just 1. So this is the same as this. So, and then as I make dynamical moves, for instance, I flip this dimer, pair of dimers. Now I've gotten to a case where there's only 2 dimers crossing it, but this e to the I pi times n is still 1. And in fact, you can see that any local moves that I make are going to change the to cross this line by an even number. And therefore, as long as my Hamiltonian is local, psi and psi prime are going to have the same energy. Now, it's not that there aren't any configurations that have an odd number here. Oh, sorry, I just made some more flips to just show you other examples. But now, suppose I introduced a non-local move. Suppose I looked at this line that goes all the way around my system, and suppose I shifted the dimers all the way along this. So I've just done that. Now what you can see is I've now shifted the number of dimers that cross this line by 1. So now I understand that this state is really a distinct state from this. In fact, it's orthogonal to this, but it has the same energy. It has the same energy. There are states that have even number that cross this line and a ground state that has an odd number, and they're exactly degenerate. And I could do that also in the y direction. So there's a topological degeneracy as long as my Hamiltonian is degenerate. All right, so let me skip this. Okay, so this, with a little bit more work, what you can show is that this state has all the physical attributes that are well understood of the deconfined phase of a Z2 gauge theory. And so what I've showed you is that it's a fluid, it has deconfined holons, it has topological degeneracies on a closed surface. I haven't showed you that it has finite energy Bison excitations, but maybe you'll take my word for that so that I can get to the end of my talk. Okay, so I guess this is the end of my talk. And so I'll skip the new stuff. And yeah, I just want to say 2 things. One is my family has recently produced 2 books that I want to advertise. One is a science fiction book that's been written by my son, and the other is a statistical mechanics text, which I hope is not science fiction, that was written by me, and I want to advertise those for you. And so thank you for your attention.
Thank you, Professor, for such a nice and insightful lecture. Now the seminar is open for questions. So, yeah, you
Hello?
can ask your questions. Yes, yes, we can hear you. Yes, I can see Manoranjan. You can ask your question, Manoranjan.
Yeah, thank you very much for nice talk, sir. I was just wondering that what kind of system, this 2D example, we can think of. I mean, is there any material or something has been where this kind of effect has been observed?
So that's a really good question. So okay, so here's the answer. There are a number of very promising spin liquid candidate materials, of which the best example is probably something called Herbert-Smithite, which is a spin-a-half system on a Kagame lattice that's studied by my colleague here, Young Lee. And it's actually believed that at least the best evidence is that this material actually is in a Z2 deconfined phase of just the sort that I described. However, the evidence isn't airtight. It's sort of the sort that if we had, I don't know, 5 or 6 materials that we knew were spin liquid, and somebody came to you with the evidence that Herbert-Smithite is a spin liquid, you would say, sure, that's really compelling. But the thing is that for the first demonstration of the existence of a new state of matter, you want absolutely incontrovertible evidence. And there is no material at present for which there is incontrovertible evidence of any. I mean, there's a whole variety of spin liquid states that have been well characterized theoretically. And for at least several of them, there are good candidate materials, but it's constantly the case that each of these materials has various, nasty material properties that have made it impossible to absolutely establish that they're spin liquids. And actually,
Yeah, I agree.
this is actually true not only of experiments, but also of numerical experiments. So we have various engineered models where we can prove that there are spin liquid ground states. But if we look at non-engineered models, such as the spin-2.5 Heisenberg model on the Kagame lattice, the numerical data is, again, suggestive that it's a spin liquid, but there seem to be many close by competing phases. So even the numerical evidence is not incontrovertible. So it's a nasty fact. You know, I think all of us who work on this field feel there must be spin liquids all over the place in material systems, but there is exactly zero in which they've been established beyond doubt.
Yeah, I agree with you. I mean, in your opinion, what are the experiment we should look for to get this evidence of the spin liquid, and we are and we should be sure that this is a spin liquid. What are the experiments you suggest?
Right.
Because
So,
most of the people look for this.
right. So one of the problems is that most of the experiments that people use, you say, I see things, and there's no other phase of matter that agrees with all of this. So it's by exclusion. And there are many complicated phases of matter, and most materials have disorder. And once you invoke disorder, it's really hard to rule out anything. So what you want is to measure something that's an affirmative evidence of a spin liquid. So there are some examples of things. So for instance, if we had as in Herbert Smithite, if we have a quasi two-dimensional system that consisted of layers of spin liquid, then you can move fractionalized excitations within the layer. So you could say thermally excite some holons and have them move around and carry current in the layer, but they can't tunnel between layers. Only electrons can tunnel between layers. So what you would find if you, say, measured the resistance in plane direction and in the perpendicular direction, that as you go down to zero temperature, the anisotropy of the resistance would diverge. So there's no other face of matter where you would get a divergent resistive anisotropy. Doesn't matter how much disorder you have or anything else. So if you could show that you had a resistance anisotropy that was diverging as the temperature went to zero, you would have proven that you had two-dimensional spin liquids. There are more complicated experiments that you could do. For instance, it turns out that a spin-on and a Bogolubov quasiparticle in a superconductor can coherently tunnel into each other. So you could have quantum interference experiments where you inject quasiparticles into a superconductor and have them coherently tunnel into a spin liquid. And so you could predict coherent oscillations that, again, would be absolutely airtight evidence of a spin liquid. These are unfortunately all very hard experiments to do, but I'm a theorist, so I can propose hard experiments.
That's right. Okay, thank you, sir.
Yeah. Do we have further questions, please? I can see a hand. Yes, you can go ahead with your question, please.
Hello, can you hear me? Can you hear me?
Hello? I hear
Can
somebody.
you hear me?
Yes, we can
Yes.
hear you. Please ask your question.
Yeah, okay. I have a question from the very beginning of your talk where you introduce, for instance, the gauge field appears as an artificial construct because you wrote the original formula product of two fields. And for instance, that is how this whole business of slave representations was built. And my question is, I mean, sort of how do we fix the physical legitimacy of the gauge field in such constructions?
Sorry, how
because
I
I see
didn't.
them being heavily used all across condensed matter, especially in the classification of.
Could you try again?
Sorry, can you hear me?
No, I hear you, but I'm having a hard
Hello,
time.
can you hear me?
Yes,
Yeah,
I can hear you,
I
but can
guess
you
the
speak a little
network at my
louder?
end is not very good.
yeah. Actually, you can just repeat your question once more. We can hear you, but you can louder and once repeat once more.
I mean, my
So you were
question
talking
is
about this
that
slide.
in the slave particle kind of representations, how no, right in the very beginning, the slave particle representations, like these part-on constructions.
Yeah, that's this. This is the slave particle construction.
So how do we? I mean, here we have this gauge sort of
Yeah, so if we wrote
field
down a
and which
field
naturally
theory of this,
appears, and the question is,
right? So if we write
yes.
down a
So
field
my
theory
question
of
is,
this,
how do we ensure that the physical legitimacy is guaranteed for this chi variable?
how do we guarantee what?
Physical.
The physical
I mean, this
legitimacy
is
is
an artificial
guaranteed.
construct. The chi is an artificially emerging entity, and how do we ensure that this is indeed physical?
Right. So that was my point. This is mathematics. If I write down what the theory looks like, it looks like a gauge theory without any Maxwell term. So it's just a pure gauge theory. So since the coefficient of the Maxwell term is 1 over the charge, that means it's at charge, or 1 over the fine structure constant. It means the bare theory that you write down by this is a gauge theory at infinite gauge coupling. So, that's meaningless.
Okay.
Now, what people do is they say, maybe when we integrate out high energy degrees of freedom, we generate a Maxwell term. And so that then at low energy, maybe we get a successful description of this in terms of partons coupled to a gauge theory. And the answer is yes, maybe, but the mathematics doesn't tell you that. You don't have any control of the mathematics. It's if the physics of the low energy system is the physics of a spin liquid with a U1 gauge theory, then this was a reasonable thing to do. The mathematics makes you think that you've done something exact and rigorous, but it isn't. At some point, there is this optimistic assertion that even though at high energy we're at infinite coupling, that at low energy we're going to renormalize onto the same sort of gauge theory, but at small coupling so that we can treat the problem in some sensible manner. And there's no proof that that will fail.
Thank you.
But there's no particular reason to think it'll succeed either.
Yeah,
Thanks.
thank you. Yeah, so do we have some more questions? Yeah, Professor, you did not tell us because it was at the end, but you were suggesting that you could have these quantum spin liquids even without spins. Can you just, in few like you can just tell something about it?
Sure. So I'm going to do this really fast. I can't tell you how long it took me to animate all of these things.
Yeah.
Okay, so so what I'm going to do is just describe to you a model that we've done a numerical experiment. So we is actually Hung Yao and his students. I'm a minor co-author on this, and they found a spin liquid. So and I think that, I said that it's been hard to find these in non-engineered models. I think that this is an example of a non-engineered model. in which we've really proven that we have a spin liquid. And so the problem we're going to look at is actually the Su-Schrieffer-Heeger model, the same model, or almost the same model that was treated in this one-dimensional system, but now treated on a triangular lattice. So here's the model. Let me just take a minute to describe what it does. So B is the hopping operator for electrons from site I to site J. The sum over sigma is sum over the polarizations of the spin. And the hopping matrix element from site I to site J is modulated by a phonon coordinate called xij, where x is a phonon that lives on the bond ij. So you could think about it like this. I have site 1 and site 2 where the electrons live, and x12 is the modulation of some molecule that bridges this bond, and as x goes in or out, it becomes easier or harder for the electron to hop from site 1 to site 2. This model has two dimensionless parameters. One is the electron-phonon coupling called lambda, which is basically tells me how strongly the phonon is coupled to the electrons. The other is the phonon frequency, which is determined by the ratio of the phonon stiffness to the mass in the usual way. And so the ratio of that phonon frequency to the bandwidth 9T of the electrons is the other dimensionless parameter. It tells us how fast or slow the phonon is relative to the electrons. This problem is a very complicated problem, but it turns out that it's something that can be treated numerically by quantum Monte Carlo. It doesn't have any fermion minus sign problems for reasons that I can describe to you. And so we can really solve it numerically very well. We're going to solve it at a density of 1 electron per site, and we find this phase diagram. So at small lambda, or at omega or high phonon frequency, we find a superconducting state, an S-wave superconducting state, as you would expect of the electron-phonon problem. At very large electron-phonon coupling, we find this staggered valence bond solid, which is an insulating state in which the lattice breaks the symmetry and forms an insulating state. But as you can see here, in the middle, we form a spin liquid state here. So this is a problem with only electron-phonon coupling. There's no magnetism anywhere. There's no repulsive U, and we find a spin liquid ground state.
Okay, yeah, thanks a lot. Do we have any other question? Okay, I think it's, if not, anyway, it's very late for you. I think it is late in the night. So
yes, it's getting there.
We are so grateful that.
Query. Just one query.
Yes.
Professor Kivelson, in this QSL phase, what is the nature of this phase? For instance, is the lattice breaking no symmetry or
no? So this quantum spin liquid state has the following properties. First place, it breaks no symmetry. So, and it's got a gap. It's got a gap to everything. It's got a gap to charge. It's got a gap to spin. It's got a gap to spin singlet excitations. If we calculate the spin-spin correlation functions, or the charge density correlations, or the superconducting correlations, they're all very short range. So it's an absolutely featureless fluid state, non-broken symmetry state, gap state, but it's at 1 electron per site. So by the Lieb-Schultz-Mattis theorem, it must be topologically ordered. In addition,
so my question is, which of these gaps is the lowest?
What? The gap that's the lowest is the gap to spin. It's the gap to spin singlet neutral excitations. So it has a collective mode with no quantum numbers, just energy.
Okay. Thank you.
So that's the smallest gap by a large factor. So, you know, this state is actually, as I said, well described as the same Z2 quantum spin liquid as is found in the quantum dimer model, the model that I just described on the triangular lattice by Mosner and Sondy. So it's almost certainly that state, but I've told you all the things we've measured. But we've also measured holon deconfinement.
Just one more question. The phonons are optical here, I guess?
The phonons
just
are optical, so that's why I say it's SSH-like. The phonons, as you can see, we've represented them by Einstein oscillators, but they're coupled, they modulate the hopping rather than the site energy. So in that sense, it's SSH-like. It's a phonon that modulates the hopping between site I and site J.
I see. Thank you.
Yeah, thank you, Professor, for such an insightful talk. And it's anyway very late for you there. So with this, Manoranjan, do you want to close it?
No, you please go ahead, and from my help, you can do that. And thank you very much, sir, for joining. Yes. And
very
hopefully,
that you could give us.
sometimes, yeah.
All right, goodbye.
Yeah. With this, we'll close this seminar. Okay, thank you, everyone.
Yeah.
And thank you, Professor. Bye.
Thank you, sir. Thank you. Good night.
Good night.
Good night.
Good night.